Hello, this is the third video in Newtonian gravity. So we have the formula now for gravitational attraction between two objects of mass MA and MB. And this is going to be divided by r squared, where r is the distance between the centers of the object, roughly, times this universal constant. Now, this is the universal constant with this value, 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared. You were already familiar with the gravitational acceleration, which was 9.8 meters per second square in the lab frame in your exams. That's the number you're used to. But that number it changes. It depends on where you are on Earth. Earth is not a perfect sphere to begin with. So, for instance, if you move towards the poles, you'll get actually closer to the center of the Earth. In addition, you have mountains and high elevation places. So you expect G to change at those places too. And here's how we'll see how G changes as you move around the Earth. Okay, so the task is now to relate these two. The G in the lab and then the universal G, which is the same number everywhere. So to do this, let's apply what we already know. We know that objects which have mass m will have a weight equal to m times g, right? This is the weight of the object. It's towards the center of the Earth. So let's say here's you standing on Earth. Doesn't matter where you are. Earth has a radius equal to RE. I have a table here for the radius of the Earth. It says a mean radius, 6,371 kilometers. Not the equatorial radius, but mean radius. It's okay, we can use it. So you're standing here. Now, you have weight, right? Let's show it as a vector that points to the center of the Earth. This is your weight, m times g. Your mass is m, Earth's mass is me, and I have it here too. Earth's mass, 5.974 times 10 to the 24th power in kilograms. So mg is your weight, but it is also this force here. Now what I'm going to do is I'm going to equate mg to the force here. M is your mass, me is mb. Now divided by, I need the distance between, your center of mass, maybe somewhere on your belly, from your belly to Earth's belly, right? That is going to be that R in the formula. But that's 1 meter here, or whatever, 1 meter, let's say, approximately, even less. That's so small compared to this 6,000 kilometers. So there's no harm in taking R approximately equal to RE. So I'm going to put RE here, RE squared. All right, and then as you see on both sides, I have m. If I get rid of those m's, the expression on the right-hand side is what g is. So let's plug in those numbers and see if we can get to 9.8. So 6.67 times 10 to the negative 11 times me, which is 5.974 times 10 to the 24th, and the denominator 6.371 times 10 to the 3 kilometers, another 1,000 to convert it to meters, so 6. And then you square that. So grab your calculator and start punching in the number. 6.67, 10 to the negative 11 times 5.974, 10 to the 24th power divided by 6.371, 10 to the 6th square. Yeah, 9.816933334. 81.7, let's say. Really close, right? So that's how you calculate the little g, the acceleration due to gravity. Now, obviously, if you're on top of the mountain here, g will be less because you're farther away from the center of the Earth. So if you're flying in a plane, if you're in the plane, g will be even less if you're at that height. So it depends on where you are and how far you're away from Earth. In outer space, of course, g doesn't mean much. On a different planet, you have a different g. Let's say you want to find the gravitational acceleration of Mars. Easy. Use the same formula, just replace the mass and the radius by the value for Mars, right there. Just find Mars here, and 6.67 times 10 to the negative 11. Okay, Mars mass is 0.1074 times Earth's mass, 5.974 times 10 to the 24th. And what about the radius? 0.532 times Earth's radius, 6.371 times 10 to the 6 squared. Actually, I didn't even have to use all these numbers in the calculation. I could just take those, let me mark them with green here. I could take these, and of course I have to square that 0.532 and then multiply it by 9.817. Let's see if it works. So 0.1074 divided by 0.532 squared, 0.379. So approximately a third of Earth's g. So this times 9.817. It's 3.73 meters per second square. Okay. So if you ever go to Mars, you'll feel lighter. All right, almost 3 times lighter. What about the moon? Moon. I'm not gonna use the numbers. Do we have moon here? We don't have, I don't see it. But I know it's 1/6 of Earth's g. All right. So you can come up with some hypothetical situations. Let's say planet X, okay? Some planet X with radius Rx and mass Mx. Let's say its mass is 0.8 Earth mass, and the radius is 0.7 Earth radius, right? Different density and all that. Density is total mass divided by volume. So what is the G on that planet in terms of the G on this planet, right? So let's say G of planet X, G of planet X will be the universal constant that never changes times mx divided by rx squared. And that is equal to G times, now mx is 0.8 me divided by 0.7 re squared. So that will be 0.8 divided by 0.7 squared times G Earth. All right, so that's the idea. So 0.8 divided by 0.7 squared, 1.63. Now you would be heavier on this planet, right? 1.63. Earth G. All right, so weight. Weight changes. It depends on what planet you're from. Mass does not change. Either think of it like inertial mass or gravitational mass. Doesn't matter. Mass is conserved. Doesn't matter where you are. Little g, just like your weight, little g is dependent on the planet. The capital G, the universal gravitational constant, does not change. Okay, I'm gonna stop here.